An encoder is a device that can convert angular displacement or linear displacement into electrical signals. A grating ruler is a type of encoder. It is often used to measure linear displacement. It consists of two parts, the scale grating and the grating reed head. Generally, the scale grating is fixed. The movement of the grating reed head is used to detect the displacement. The grating reed head is composed of a light source and a lens, an index grating, photosensitive elements, and other components. Among them, the index grating is a relatively important part. It directly determines the measurement accuracy of the grating ruler. The measurement of the grating ruler utilizes the Moore fringe phenomenon generated by the grating. A grating is made by engraving a large number of parallel and equidistant marks on glass. The marks are the opaque parts. The slits between the marks are the light-transmitting parts. For a refined grating, several thousand or even tens of thousands of marks can be engraved within a width of 1 centimeter. Moore fringes are the visual effects of interference between two lines or two objects at a constant angle and frequency. In 1874, British physicist Rayleigh first revealed the scientific and engineering value of the Moore fringe pattern, pointed out the possibility of measuring the relative displacement of the grating by observing the movement of the Moore fringes. How are Moore fringes used in a grating ruler? Suppose we want to measure the displacement x. Then, as long as we know the grade width d of the grating and the number n of the moving grades, we can obtain the value of the displacement x. How should the number of moving grades be calculated? Suppose there is a fixed point. When the light passes through the grating and projects onto the fixed point, due to the movement of the grating, the change of the light at the fixed point is alternating between light and dark. By recording this change, we can know the number n of the moving grades. However, the slits on the grating are very narrow, and it is difficult to distinguish the light and dark changes at the fixed point during movement. If we can magnify this phenomenon, the problem can be easily solved. Moore fringes have such a magnifying effect. The distance between two bright fringes or two dark fringes in the Moore fringes is called the width of the Moore fringes, denoted by W. Let the deviation angle between the index grating and the scale grating be theta, and the grade width of the index grating be d. The arrangement direction of the Moore fringes is perpendicular to the bisector of the angle between the two grating lines, and the value of the width can be expressed. Suppose d equals 0.01 m and theta equals 0.001 rad. The obtained value of the width is 10 millimeters. That is, the grating is magnified 1000 times. Whenever the grating moves by 1 grade pitch, the Moore fringes will pass through 1 fringe pitch. The fixed point, that is, the photosensitive element in the reed head, will experience a cycle of change. In this way, the periodic optical signal can be converted into a sine signal or a square wave signal, and the number n of the moving grades can be obtained, so the displacement of the object can naturally be calculated. Through the above method, although the moving distance of the object has been calculated, but how can we determine its moving direction? We can place 4 photosensitive elements in the reed head, namely a positive, B positive, a negative, and B negative. The output signals of each photosensitive element differ by a quarter of a cycle. Subtracting a negative from a positive gives the A signal, and subtracting B negative from B positive gives the B signal. When the A signal leads the B signal, the ruler body moves forward. When the A signal lags behind the B signal, the ruler body moves backward. The A signal and the B signal have the function of preventing signal interference. When the rising edge of the A signal arrives, and the system does not receive the rising edge of the B signal, the system will not count. or when the signal is interfered with, and two rising edges are generated. The system will also eliminate this interference, because when the system receives the rising edge of A, it will check whether the rising edge of B arrives, and will not count the other rising edge of the signal. The signal and the B signal can also improve the accuracy of the grating ruler. In a complete signal cycle, the signal will generate one rising edge and one falling edge, and the B signal will also generate one rising edge and one falling edge. Whenever the rising edge of the signal arrives, the system counts once. This is the single frequency multiplication, using the accuracy of the grade pitch of the grating ruler. When counting the rising edge and the falling edge of the signal, respectively, it is the double frequency multiplication, which divides one grade pitch into two parts. When counting the rising edges and the falling edges of the signal and the B signal, respectively, it is the quadruple frequency multiplication, so that the grating ruler can measure more precise displacements. The accuracy of the grating ruler refers to the manufacturing error of the grating ruler. For example, plus or minus 0.275 micron per 10 mm, which means that the possible error for a movement of 10 mm is plus or minus 0.275 micron. It should be noted that an accuracy of plus or minus 0.275 micron per 10 mm cannot be deduced to plus or minus 2.75 micron per 100 mm, and there is no such linear relationship between them. The resolution marked on the grating ruler is generally obtained through frequency division, including the physical frequency division introduced above, and an electronic circuit frequency division method. When the grade pitch of the grating ruler is 25 micron, whenever the ruler body moves 25 micron, it will output one cycle, after being subdivided 50 times by the circuit. For every 25 micron movement of the ruler body, it will output 50 cycles. That is, the resolution set by the manufacturer is 0.5 micron. When the movement of the ruler body does not exceed 25 micron, the read head will not output a cycle. Let's summarize the characteristics of the grating ruler. It has a high detection accuracy, and can reach a resolution of 0.1 micron after subdivision. It has a fast response speed and can realize dynamic measurement, which is beneficial to automatic control. It has high requirements for the environment and is afraid of oil stains, dust, and vibration. It is difficult to install and maintain and has a high cost. The structure of the encoder and the grating ruler is not very different, and there are many common points in many aspects. Next, we use a data acquisition card to collect the displacement data of the grating ruler. The equipment used in the experiment is a grating ruler and a USB 3313 data acquisition card. First, explain the specific parameters of the grating ruler. Its defined stroke is 200 mm. The maximum measurable distance is approximately 220 mm. The grade pitch is 0.02 mm, and the accuracy is 0.005 mm. The pin definition of the grating ruler: red 1, connect to positive power supply; black 2, connect to negative power supply; green 3, defined as a phase signal; white 4, defined as B phase signal; orange 5, defined as C phase signal. Now start wiring. Connect the CT0 SRC port of the acquisition card to the phase. Connect the CT0 gate port to the B phase. And connect the CT0Z to the Z phase. Since the grating ruler provides a power plug, connect the GND terminal of the grating ruler to the DGND terminal of the acquisition card. and connect the positive pole of the power supply to the positive pole of the grating ruler. Finally, connect the acquisition card to the computer. Open the latest version of the DAQ software. Click Coder and start setting the parameters. Set the sampling rate to 10,000. Select channel CT0. Select the encoder type Codex 4, which means that each signal cycle can have 4 increments or decrements, corresponding to 4 increments or decrements of the measurement step in each cycle. In the unit conversion, set the value represented by each pulse to 5. With the unit of μm, click Next. Do not check the data storage. Select Immediate Trigger and click Finish. Set the abscissa of the software to 0 to 10,000 and click Start. The starting position of the grating ruler is 0, and when sliding the grating ruler, you can see the software displays the data information of the grating ruler. On the right side of the software, you can directly read out that the grating read head has displaced 224.115 mm. When moving the grating read head quickly, you can see the waveform change accordingly, and even a slight movement will be reflected in the waveform diagram.